So we're in 6.1 part 2. So we're going to talk about the ambiguous case with the law of sines. So yesterday we used law of sines for angle side angle and angle side triangles, and to find our missing parts, to solve our triangle. And we mentioned that we can use law of sines for side angle triangles, but something interesting happens with side angle triangles. If you remember back to geometry, when you were studying congruent triangles, that side a was not a postulate or was not a theorem that you could use to prove that two triangles were congruent. Let me draw a picture to say why that is the case, and then we'll talk about what we have to do when we have that situation. So for a side angle triangle, let me draw one up here. So let's say we're given angle A. So this angle is not going to change. And we'll call this side B, angle B, and side A and side B. So we know angle A, so this angle is not going to change. We know side B and we know side A. What can happen here is I can rotate. So right now we have a nice triangle. If I swing this, if this is like a hinge, and I swing this around in a circle, it can swing around and contact the side down here, and this would also be length A. So this is angle A, side B, and side A. So here's a side angle triangle, and here's a side angle triangle, the smaller one and the bigger one, that have the same angle, angle A, the same side, side B, and the same side, side A. So in the right circumstances, I can end up with two possible triangles with a side angle triangle. And we'll also talk about another possibility, a couple of other possibilities for side angle triangles. But this is why we call it the ambiguous case, because we can end up with two possible solutions to our triangle. We can get an angle B here. We can also get this angle B here. So we can get those two possibilities. So let's go through what happens with a side angle triangle. So we have three cases for an acute triangle and two cases for an oblique or for an obtuse triangle. So let's draw our first case. Our first case, we're given angle A, side A, and side B. I'm going to draw it this way to kind of exaggerate. And I'm going to suggest when we have a side angle triangle that you always draw it in this configuration, no matter how your sides are laid out. And this is going to be angle B down here if it connects. So in a case like this, if A is less than B, this angle can't change. If A is less than B, it can't connect with this base of the triangle down here, so I get no triangle. So that for this particular case, we don't even get a triangle. If A is too small, this angle doesn't change, this side doesn't change, so this has to stay the same. We can't make a triangle. So let's look at another case. I'm going to draw my triangle this way. So there's angle A, there's side B, and there's side A, and I have a 90-degree angle there. Well, in this case, what I'm going to do is on this first one, I'll draw it in, and we'll do it here on the second one as well. So I'm going to draw in the height like we did yesterday when we came up with the law of sines. I'm going to do that on my right triangle here also. So there's my height in red. Well, in this case, side A equals the height of the triangle. If this side equals the height of the triangle, then I have one right triangle. And if you remember back to geometry, the theorem that you used that was related to right triangles was hypotenuse leg. So here we have the hypotenuse and a leg of the triangle. So in this case, we do get one triangle. How do we find the height of these triangles? How did we do it yesterday? The height of the triangle is, this is a 90-degree angle. This is the opposite, and this is the hypotenuse. So we said the height was B sine A. So we can always find the height of these triangles by, if we're drawing them in this situation, the height equals B sine A. So if this side equals the height of the triangle, we get one triangle. Here's a third possibility. I'm going to draw the triangle like so. There's A, there's B, and I'll draw in my height just so we remember it's there, because that'll be important with these kinds of triangles. For this one, I'm going to say A is greater than B. If A is greater than B, if I swing this around, it's going to miss on this other side, so it can't make another triangle. So if A is greater than B, this side is larger than this side, then we only get one triangle. So if I swing this around, it's too big to connect again over here, so it's going to miss. We'll get one triangle if A is greater than B. Well, here's where things get interesting. This is the example that I drew up above. So there's A, B, A, and angle B. And let me draw my height in as well. And this is the case where I can swing this around and connect this to make another triangle. And that is also side A. In this case, A is larger than the height, but smaller than side B. So the height is less than A is larger than the height, and A is less than side B. So side A is between the height and side B. In this case, we get two possible triangles. And this is the one we call the ambiguous case, because we get two answers. So we get two possible values for angle B. I can get this angle here for angle B, and I can also get this angle here for angle B. For each of those values of angle B, I get a different possible value for angle C. I can get this small angle or this big angle. And I get two possible values for side C here. Get the long side or the short side. So when we have the ambiguous case, when A is larger than the height, when this side is larger than the height, but smaller than this side, we have two possible triangles. And we have to figure out these two possible angles. So looking at this diagram, can we figure out how this angle B is related to this angle B? So we're looking at this angle and this angle, trying to figure out how they're related. Anybody see how those two would be related? Is that what you were going to say as well? Supplementary. So this triangle here is an isosceles triangle. This is A and this is A. So those two angles have to be congruent, and those two are supplementary. So the two possible values for angle B are supplementary. So we would use the law of sines to figure out one value for angle B, and that would give us a value for angle C, and then we could find side C, and then the other possible value for angle B would be supplementary to that first one we found. Then we would use that one to find the other possible value for angle C, and that would give us a second possible value for the side of this triangle. So we get the big side or the short side. So that's when we get the ambiguous case. When A is larger than the height, but smaller than the side of the triangle. So those are our four possibilities when we have an oblique, or an obtuse triangle. An acute triangle. Nothing larger than 90 degrees. So with side-side angle triangles, this only happens with side-side angle triangles. Ambiguous case, only possibility with side-side angle triangles. What I recommend is draw your picture so that it's in this configuration. Just makes it easier to visualize. Drawing the height and calculating the height is really the key. So knowing the height of the triangle. And then you decide, if you have a side-side angle triangle, do you have no triangle? This isn't big enough to connect. Do you have one triangle? Or do you have two possible triangles? And then you use the law of sines to proceed from there. So questions on those possibilities and how they work out. Okay, again, side-side angle triangles, that's the only ones we have to worry about. Find the heights and find how your sides compare to the heights into each other. Yes? Yes. All right, let's look at what happens with an obtuse triangle. There's less possibilities with obtuse triangles. We're still talking about a side-side angle combination. So let me draw an obtuse. We'll make angle A be our obtuse angle. So there's angle A. I'm going to exaggerate it here. There's A, there's B, and this is going to be angle B if it connects. So if we have an obtuse triangle and if A is less than B, can I make a triangle here? No. So I get no triangle. And then my only other possibility is if I have it set up like so, and my triangle would be like this. And this is A, B. If A is greater than B, how many triangles do I get here? Can I rotate this around and get it to connect to this side anywhere else? This is really the only place it'll connect. Let's swing it all the way around and we'll get back to there. So I only get one triangle. So if we have an obtuse angle in a side-side angle triangle, there's either no triangle if this isn't long enough to connect, and one triangle if it's larger than, if this side is larger than this side. What happens if side A equals side B in this situation? What do I get there? Do I get a triangle? It's not completed. I get basically these two sides would overlap here, and I would just get an angle. Because A and B would overlap if A equals B. It would touch like that. So no possible triangle if A equals B. So we either get no triangle or one triangle. I guess we could say if A is less than or equal to B. So questions on the ambiguous case? Nothing really different that we do once we figure out that we have the ambiguous case. We just have to go through the law of sines twice for the different angles to figure out if we want to solve, if we're looking to solve our triangles. The difficult part, not really difficult, is just deciding, do I have the ambiguous case or do I not have the ambiguous case? Can I make a triangle? Can I not make one? Can I make two? And again, only with side-side angle triangles do we have to worry about this. All right, so let's go through a few examples. So for these, we're not necessarily going to calculate, go through and solve, find all the missing pieces, because once we figure out what case we have, then we're just back to using the law of sines and calculating just like we did in the homework last night. So let's go through a few examples. So let's say we have A equals 26 degrees, B equals 5, and side A equals 21. And we want to solve. So I'm going to draw this. So because we have a side-side angle triangle, we have two sides in an angle. This is SSA. We need to check, do we have the ambiguous case? So I'm going to draw this out. And when there's a possibility of an ambiguous case, I always draw them out without connecting, because we're not sure yet. All right, so we have A greater than B. Here we have this side greater than this side. How many triangles can we get? One. And if we weren't sure, we could find our height. We want to make sure it's larger than the height. Our height is 5 sine 26. Well, how big is 5 sine 26 going to be larger or smaller than 5? Smaller, because the sine is always, sine of an angle is between -1 and 1, and we have a first quadrant angle, so it's going to be between 0 and 1, right? So this is going to be less than 1. So our height is going to be less than 5, so this is larger than this side. 21 is larger than 5, and 21 is larger than the height. So 21 is greater than 5. 21 is greater than the height. So we have one triangle. And we can just proceed with the law of sines, just like we've done before. So I would find side B, or find angle B using the law of sines. That would let me find angle C, and then I could find side C. I'm not going to go through that. We did that yesterday. We know how to use the law of sines. From here, we would just use the law of sines. Questions there? All right, let's take a look at another one. So let's say we have b equals 78, c equals 12, and side b is 5. We want to find angle C. So I'm going to draw out this triangle. I'm going to put my angle B here. So this is 78 degrees. This side is 5. I'm going to call this side 12, and angle C would be down here. And because we have a side-side angle triangle, this is side-side angle, I want to check to make sure that we're going to get a triangle, 1 triangle, 2 triangles, or 0 triangles. Well, 5 is less than 12, so we have to be a little more careful here. What I'm going to do is calculate the height. So the height is 12 sine 78 degrees. We could plug it in our calculator, but let's think about it for a second. As we get closer to 90 degrees, the sine of our angle gets closer to what? 1. So 12 sine 78 is going to be pretty close to 12. It's going to be a little less than 12, but it's going to be pretty close. So I'm going to say this is approximately 12. We're pretty close to 12. Did someone calculate it out? What does it come out to?
11.
It's like 11.7, I think. So this is approximately 12. This side is smaller than the height. What does that tell us? 5 is less than h. So I cannot make a triangle. This one's an impossible triangle. This side can't swing down here and connect with the base. Now, if we could go through and kind of do this the brute force method. So let's look at what would happen if we did the brute force method. I'm just going to apply the law of sines to this. I'm going to say sine C over 12 equals the sine of 78 over 5. So I get sine C is 12 sine 78 over 5, or sine C is about 2.35. So what does this tell us? If you tried to find the inverse sine of 2.35 in your calculator, what would your calculator tell you? Error. Because there's no angle that has a sine of 2.35, right? The sine of an angle is between -1 and 1. So this would get, if you plug this in your calculator, if you were just going to go through and do this, the brute force method, plug this in your calculator would, when you try to find angle C, find the inverse sine of 2.35, you would get an error. So there's no possible angle C that has a sine of 2.35. So this would tell you no triangle. So two different ways of looking at this problem. So if your calculator gives you an error when you have a side-side angle triangle, that might be a hint that you need to look at what's going on there a little more carefully. So questions on that example? So that's one possibility. You might not get a triangle with a side-side angle triangle. Okay, let's look at another example. Let's say that A Angle A is 29 degrees. Angle, sorry, not angle, side A is 6, and side B is 10. We want to find angle B. So this is a side-side angle triangle. Tells us maybe we have an ambiguous case. Maybe we don't even have a triangle. So let's draw out our possibility here. I'm not going to connect until I know for sure. This is 10, this is 6, and angle B would be down here. All right, so 6 is less than 10. We need to figure out how 6 compares to the height of the triangle. So let me draw my height here. Our height is 10 sine 29 degrees. Now this one is a little less easy to kind of intuitively know how big sine 29 is. 78 was close to 90, so we were pretty confident that the sine was close to 1. So we're going to calculate this out. So our height comes out to be, when we plug this in our calculator, is about 4.85. So 6 is greater than our height, and it's less than this side of the triangle. So what does that tell us? We have two possible triangles. So 6 is greater than h. 6 is less than 10, so we have two triangles. So we use law of sines to find angle B, and then we would know that the second possibility was supplementary. So I would say sine B over 10 equals sine 29 degrees over 6. So sine B is 10 sine 29 over 6. And what does that give us for angle B? Someone calculate that out. 53.9. So that's one possibility for angle B, and that triangle would look like something like this. And then our other possibility is the supplement of 53.9. So I'd say or B equals 180 minus 53.9, which gives me, what does that come out to? 126.1. And that triangle would look like something like that. And this angle would be 126 degrees. So those would be our two possible triangles for this situation. Then we would end up with two possible values for angle C that we could find because our three angles had to add up to 180. And we'd have two possible values for length C. We'd have the long one and the short one. So questions there? All right. So ambiguous case, not really anything, not necessarily difficult, just something we have to be aware of. With the side-side angle triangle, we need to be aware that we could have the ambiguous case. We could have no triangle, we could have one triangle, we could have two triangles. And we just have to do our checking to make sure which situation we have. All right, the last thing I want to talk about today, last thing with the law of sines, is using law of sines, or using something related to law of sines to find the area of an oblique triangle. we come up with a nice area formula. So let's draw a triangle, just like we did for when we came up with the law of sines yesterday. And I'm going to draw in, like we did yesterday as well, draw in our height. All right, so what's the area, how do we find the area of any triangle? Area equals 1/2 base times height. So let's apply that formula to this triangle. So our area equals 1/2. What's the base of this triangle? What's the length of the base? AC or B is that length? 1/2 B times the height. Well, how did we find the height of the triangle yesterday? Or how did we find it today? C sine A. I'm going to plug that in here. So the area equals 1/2 BC sine A. I could also find the height from this triangle, and I could say that is 1/2 AB. Here my height would be A sine C, AB sine C. I could draw in the height to another side, and I could also find that the area is 1/2 AC sine B. So all three of these formulas are ways that I can find the area of an oblique triangle if I have, you notice what we have, BC sine A, so we have these two sides and this angle, AB sine C. We have two sides and the angle between them. So if we have two sides of a triangle and the angle between them, we can use this formula to find its area. So just a nice little formula related to the law of sines that we can use to find the area of triangles. Block day, when we talk about law of cosines, we'll come up with another area formula where all we need to know is three sides of the triangle. All right, questions for today? Just extending the law of sines a little bit. Okay. Homework. There you go.